welcome back or still here. I'll do the introduction because I know there's a couple people that weren't here before. My name is David Brown, I'm at Lenaro, and I've been working on Rust on Zephyr for about, I don't know, 6-7 months, something like that. Just gave a talk. If you missed it, they'll be available. The slides are online if you want to look at them and the status of where we're at. I want to take this time slot to talk about this very overly zealous, wonderful title of why Rust and Zephyr are a good fit. This came after asking questions, which was basically, why would if there's a Rust embedded and I can just run on top of the HAL and there's an executor that lets me schedule async tasks, why would I use Zephyr? So you can look at Kate's talk if you want the answer to why Zephyr is helpful. Yeah, there's Rust HALs. If you happen to have one of those few parts and boards that it works on, it works great. But there's a lot of hardware that's supported by Zephyr. There's an ecosystem. There's all this stuff. And at this point, it's pretty useful to be able to have access to a lot of that stuff. So where are embedded systems at today? We have demanding workloads, lots of CPU time, high concurrency, critical needs for safety, security, limited resources. This is very bullet point, almost like somebody used AI to write these points. So where are we at? One of the interesting things we have with Zephyr is you have this kind of spectrum of types of devices that it runs on. I build keyboards as a hobby, and I'm using a RP2040. It's a Cortex M0 Plus. There's actually two of them, but it's not really SMP, so I'm using one of them, and it works great. And sometimes you find, when I first was doing this stuff with Zephyr, if you're a little naive and just try to throw things together, it's like, oh, I don't have that much memory. My processor's too slow. To, really high-end things where we have processors that run at hundreds of megahertz for a microcontroller and have, megabytes of RAM and this kind of stuff. And all this kind of spectrum in between. And we still have this need for safety and security and concurrency. And there's a lot of these things that Rust has this kind of same list of bullet points of, it helps you with these things. You've heard that term, fearless concurrency, memory safety without a garbage collector, and that kind of thing. So can we leverage the two of these together? So here, look at that. I should read my slides. I should have the second one up ahead. What Rust brings to this picture is a lot of these problems, you can't write the wrong code. Now, it doesn't mean that, oh, look, it compiles, of course it works. What it means is, oh, look, it compiles, I don't have unsafe keywords, I'm not going to get a seg fault. I won't have a buffer overflow in my code, or at worst case, I'll have a runtime error with a buffer overflow instead of it just stepping on somebody else's pointer. And for the most part, that's done without a runtime cost. I've actually been shocked, per se, at how high a level my code feels like it is to have it just come down and generate really nice low-level code that, to put it simply, I was surprised when Rust was the entire thing in the picture that, like, code to toggle a GPIO just did register writes to the GPIO register in the Rust code. Of course, when you bring in Zephyr, you get some overhead, and there's an abstraction layer there where that doesn't happen. But, at least with Rust, we have really tight control over the memory and the CPU. Now, Zephyr's strength, we have this kind of small, scalable RTOS. Scalable being a big word because, as I mentioned, you have these little Cortex M0 things, you have these really powerful processors, and you can turn things on and off. The big thing there is preemptive scheduling. All of the Rust embedded stuff from, or at least not all, most of the kind of bare metal type of Rust embedded, it does do cooperative scheduling with async, but preemptive scheduling is kind of a little harder to do, and there's definitely applications for that. Zephyr also brings massive peripheral and board support. There's just an enormous amount of code. Sure, there may be a HAL out there by some vendor to support their board, but somebody's put the effort into at least making that work inside of Zephyr. And realistically, if Rust really becomes popular, this may not be much of a strength in 10 years because people will have written HALs that support these things directly from Rust. But right now, you got a lot of things that you can do when you have Zephyr because there's all that code that's already there. And it's used in the real world. You've got people actually running things on Zephyr, lots and lots of boards. So what's common here? Well, predictable performance, this kind of nice concurrency, reliability. That, we get back to that, what can we get from both of these? Can we combine them in such a way that we get the best of both worlds? And what I want to talk about is this thing called Rust async. So what is it? Excuse me. I'm still getting over this cold, sorry. In Rust, there's a mechanism called async. This was kind of started in the kind of back-end server type of world where you have a system that might need to listen to 5,000 sockets, and it's not practical to spawn 5,000 threads on Linux. And what async gives you is you get to write code that looks like ordinary Rust code, except it compiles it into a state machine. And the data is part of this structure now instead of on the stack. And every time the code gets to where it needs to wait for something, it actually just returns. And then it can be continued later when that thing it was waiting for is available. Turns out this works really nicely in an embedded environment where we have scheduling overhead. So Zephyr is great. There's a scheduler. We can have multiple threads. But the cost is that you have to have a stack for each of those threads, and the context switch is kind of expensive. The async executor is this thing that drives the work forward, and it's just a function call. It's through a function pointer, but you have this thing that does the next piece of work for a given thread, and then a thing called wake up that tells the executor that, oh, well, this thing, you might try running it again. But it's really tiny. There's no background things. There's not all this complex threads that you might think of if you remember back in the days when the Go language first started with their green threads, and there was this vastly complicated, it's like an operating system scheduler for the green threads that was mapping between the Go routines and your actual OS threads. This one, you're kind of explicit about it. Here's my async threads. Oh, run that there. And it runs one per Zephyr thread. So the difference here, we have, let's just do this vertically. So in Zephyr, when you have threads, they're preemptive. So at different priorities, a higher priority thread is available. It interrupts what was running and runs the new thread. That's the primary reason that you need separate stacks for them. The consequences is a context switch because it can happen at any time. You have to save the processor registers, that kind of thing. And it's actually this RAM for the stack that really is the most costly part of this thing, that your stack has to be able to hold all of the call frames for the deepest call tree that you have in that thread. And every thread has to do this. These threads are also isolated, is another thing. So now with async, they're cooperative. Now what that means is when a given async task is running, it's not interrupted. We'll get to the caveat in that in a minute. It just runs until it says it needs to wait for something, and then it might decide to go do something else. But that context switch is minimal overhead because it's literally just returning a value at that point that says I need to wait. And then the executor just calls the next one as a function call. But what that gives us is now we're running all of these potential tasks on a single thread, which just needs enough stack space for the deepest call chain within a given async operation. So it's kind of weird to explain. The stack size that's needed is the deepest call chain before it hits an await point, because the compiler will take any state and data that needs to be preserved across an await point and it puts it in a structure that doesn't live on the stack. They're not heap allocated, but they live in NRAM. And as such, the stack doesn't generally need to be any bigger than it would be if you were just running a single thread. And then you get a little bit of extra overhead as you make each of these tasks that run in async world, they have their data that's associated with them. It ends up being that for a typical example, I did some benchmarking between the context switch of Zephyr and the async in Rust. And in Zephyr, I could make, maybe a dozen threads if I have quite a bit of memory, because they all need a bunch of stack, and you do these benchmarks. I had no problem making 500 async tasks to go there, because it turns out, like depending on what it does, it might be 28 bytes of state that it stores. It's not storing registers, it's not having to store any of that. It's just whatever context is saved between them. And so you get a lot of efficiency out of that. So the question is, how do we combine these two? I like the sound of both. There's a need for both. Well, it turns out it actually works pretty well. So at the top we have Zephyr threads in a typical system I might build. And I'm going to pick two of these threads here, and I'm going to start an async executor on them. Then in my code, I will fire these async tasks. I have no idea why those lines are thicker. That's really weird. They're not thicker here. These tasks then will all run cooperatively on this thread, and these tasks here will run cooperatively on this thread. Now, you might ask the question, how would you know what to put where? And I mean, the kind of deeper answer behind that is, well, that's why embedded engineers get paid a lot. That's kind of back down to this is embedded system design. You just have another tool available to you. But I mean, it typically comes down to really it comes down to what are your deadlines. So things that have shorter deadlines need to run at higher priority. And can you group them together? As an example, in the keyboard firmware I'm writing, I ended up just needing two. You have most things that are short deadlines, and then I have one thing that's slow. For example, if something needs to run computation, it's cooperative, it can't interrupt while it's doing that computation. So run it at a lower priority, the preemptive scheduler can then invoke it later, or can interrupt it to do something that needs to happen more urgently. So here's a good summary of what I just said. The threads give you preemption, priority, and isolation. Async gives you this lower cost concurrency, and that you can do more things. Just my personal story, back to my keyboard firmware again, because that's where my real experience with actually using this comes from. When I started, I had one main loop that ran once a millisecond, and it just kind of plowed through calling dozens and dozens of things to go do processing. And I started to get to the point where I was running out of CPU performance on my little processor, just because it was doing all these things once a millisecond, whether it needed to actually do them that often or not. By changing this to be a bunch of little async things that communicate by sending messages back and forth, they only run when they're actually needed. And I got down to where a typical use was just using a couple percent of my CPU instead of 100% of the CPU. And the neat thing is that when you stop typing, the CPU just drops to 0 because nothing's happening. It's that interrupt from the device that triggers the first cascade of things that start running and communicating. The big thing is that in your design, if you have both of these available, you use whichever one is appropriate. You don't have to do it with just threads or just async. Maybe both make sense. How do you decide? Well, threads are kind of about deadlines and actual parallelism. That's assuming if you had like an SMP system, you would need a thread to run it, because a bunch of asyncs on one executor is still only going to run one thread. Async is good when you have to like wait for a bunch of things, whether that's messages or actual I/O, because both of those are the case. It's fine to just make short little things that just wait, because it gets rid of most of that overhead for you. But the important thing is you can run multiple executors at different priorities depending on the design of your system. So here's my practical real-world example that I just explained. When I started, big thread, 100% of CPU. So I have one executor that for things that don't take very much time, that are kind of I/O driven. And then there's a lower priority thread that runs the steno dictionary lookup. And just as an example, that lower priority thread was taking on the order of 20 to 30 milliseconds to do a lookup. And once I got the async things only running when they were needed, that thing now takes less than a millisecond, because it's actually not that CPU intensive. And then it's more complicated than that, because it tends to get to just run now. There's not cache contention. There's a lot of complexity as to why it works better now. So what I would say as a conclusion from that is, hey, let's use them together. Kind of an interesting caveat is the contract that got me doing this Rust on Zephyr was kind of explicitly, oh, we don't want async. So I threw together an async executor just kind of when I was bored. I wanted to see how complicated it was. And as I mentioned, it's probably a dozen lines of code. It's very straightforward. Most of that is because the Embassy project has an executor that they've written that is general, and it's very easy to just plug in. Here's how you go to sleep. Here's how you wake it up, and that's all it needs. So there's a semaphore in there. But as I mentioned, there's more work needed. It would be nice if these work together really well. That a driver can say, hey, Zephyr inside is using a semaphore to know when this device is ready. I'd like to asynchronously wait on that. And that's kind of the biggest thing. There's a couple of ways I can do that. The simplest way is there's a mechanism called kpoll in Zephyr, where you give it a list of, I'd like you to tell me when any of these semaphores has data available on it. If you want more efficiency, we modify the semaphore code in Zephyr to understand the concept of an async waiter. And it basically is just told, it's like, oh, by the way, when somebody gives to this semaphore, just call this function. And I haven't yet tried to push the boundaries of how well that will be received. I think having that presented as an alternative that's more efficient will be easier to sell than, no, we have to do it this way. That's pretty much it I've got for that. I just kind of wanted to give a little bit of time. If you have any questions about this or any other aspects of this work, let me know.
Last time I looked at using Rust in an embedded context, which was a while ago, it was difficult to tell how much stack size a function was going to take. So you say that you only need as much stack size as you're going to reach, but how do you know what that number is?
So there's kind of, let's start with a Zephyr answer to the question, is you turn on this stack analysis module. There's a feature in Zephyr which enables the stack. It basically sets a marker, and then periodically it wakes up and it sees how much you've actually used. As long as you can get your system to kind of do the worst case thing, that works. Typically these things are kind of deterministic, so that's not that difficult to do. I'm not aware of great like profiling tools in the Rust tool chain to kind of show stack usage and that kind of thing. I mean, I've actually gone so far as to hack things up with size of on async things, because that's actually a piece of data that you can ask it how big it is. But yeah, there's not a great answer for how much stack do I need. It's similar to if you're using an executor, how big are all these how big are these things? Each task has effectively a piece of global data that needs to be stored somewhere. Yeah, how much space needs to be allocated for them, and depending on if you're using the Embassy executor, they come out of a pool, and you have to guess how big that pool is going to be. Or you enable the nightly compiler where it just allocates them statically. And the easiest solution is to enable the nightly compiler, build it, and then use a script that reads through your build and tells you how big they are, which is what I ended up doing with that. But no, there's not a great solution for the stack size thing.
Okay, thank you.
And it's worse when you are on something like Zephyr, which readily supports multiple targets, and then you discover it's like, oh, they're actually different. And I've had like my benchmark thing that creates all those different tasks and everything. It's like, well, what size do I make the stacks? And I actually have conditional compilation based on whether it's a 32 or 64-bit target. So anyway, thanks for the question. Anything else? I think that's it. So thank you everybody for attending.